captions in English, please. So this is the third video on chapter 12. It's on electronegativity and polar bonds. So why oil and water don't mix? So you've all observed that if you combine oil and water in a container, they separate into distinct regions, right? Why? Something about water molecules causes them to bunch together into one region and expel the oil molecules into a separate region. So they are pushing each other out and excluding each other out. So this is a model of the molecule of water. The red sphere is the oxygen, the white spheres are the two hydrogens. And so water has two bonds between O and H, and they each consist of an electron pair. So the bond is made by an electron pair, which are two electrons shared between the oxygen atom and the hydrogen atom. And so the oxygen and the hydrogen atoms each donate an electron to this electron pair. So these two electrons, one comes from hydrogen, the other comes from oxygen. However, they are not sharing them equally. Even though they each provide one electron, they don't share them equally. And the oxygen atom takes more than its fair share of the electron pair. And this is a property that we call electronegativity. The electronegativity is the ability of an element to attract electrons within a covalent bond. And the value of the electronegativity is assigned using a relative scale on which fluorine, the most electronegative element, has an electronegativity of 4.0. And the larger the number, the larger the electronegativity. So oxygen is more electronegative than hydrogen, which means that on average, the shared electrons are more likely to be found near the oxygen atom than near the hydrogen atom. It's like, let's say hydrogen and oxygen are two people in a bed sharing a blanket. And the oxygen is pulling on the blanket and getting more of the blanket than the hydrogen, right? You can visualize this like this. And so this property of electronegativity is given in tables. So you will be provided with this electronegativity table on a reference paper. And it's typically given for each element in the periodic table. So if we look at the key, it goes from less than 1.5, and really the smaller value is 0.7 up to 4.0. And it's Linus Pauling, the scientist who established that, introduced the electronegativity scale that we are still using today. And he arbitrarily set the electronegativity of fluorine at 4.0 and then computed all other values relative to fluorine. And so we have this table. And it's color-coded to show how non-metals, especially nitrogen, oxygen, fluorine, and chlorine, are the most electronegative elements of all. And then the yellow ones on the opposite corner of the periodic table, where you have lithium going down to francium and going up to uranium, are the elements with the smallest values, from 0.7 to 1.4. And you can see that in between, the light blue represents elements with an electronegativity between 1.5 and 1.9. And then the darker blue represents elements with the electronegativity between 2.0 and 2.9. So we really see how electronegativity increases along a period, so from left to right, and then increases also from bottom of the periodic table to the top of the periodic table. So non-metals are more electronegative than metals. So when two elements with identical electronegativities form a covalent bond, they share the electrons equally. Because both atoms have the same electronegativity value, then they will pull the electrons with the same strength, and so the electrons will be shared equally. The example here is Cl2, chlorine. The two chlorine atoms share the electrons evenly, and we call this a pure or nonpolar covalent bond. So you need to say both pure and covalent bond. In case of a large electronegativity difference between the two elements in a bond, such as what normally occurs between a metal and a non-metal, the electron is completely transferred and the bond is ionic. So a typical example is NaCl, sodium chloride, salt, where sodium completely transfers its electrons and gives it away to chlorine, and chlorine grabs it and becomes a negative ion. And so this is then ions bonded together, and that's why we call this an ionic bond. So ionic bonds happens when there is a large electronegativity difference between the bonded atoms. And so if you have an intermediate electronegativity difference, then you will obtain what we call polar covalent bonds. So covalent bonds that contain an unequal sharing of electrons are called polar covalent bonds. The polarity of the bond depends on the electronegativity difference between the two elements in the bond, and also depends on the length of the bond. So for a fixed bond length, the greater the electronegativity difference, the more polar the bond. And here the example is HF, hydrofluoric acid. It's fluorine bonded to hydrogen, and fluorine has an electronegativity of 4.0 and hydrogen has an electronegativity of 2.1. That's a difference of 1.9. It's a large difference, and so this is considered a polar covalent bond. Fluorine attracts the electrons toward itself much more strongly than hydrogen. So we've been through those different types of bond, but really you have to see this as a continuum. It's not hard boundaries between these different cases. You have cases where we have pure covalent bonds, and that's typically between atoms of the same kind, right? Then the sharing of electron is equal between the two atoms, but also, you know, between carbon and hydrogen, or any elements that have the same electronegativity value. Then if you have elements that have that start to have more and more difference in their electronegativity value, then you move towards polar covalent bonds. And if the electronegativity is such that, you know, the most electronegative element pulls on the electron and completely grabs it, then you have an ionic bond. So it's a continuum. You have, you know, types of bond in between those cases. And so the larger the difference in electronegativity, that's represented by delta En for difference in electronegativity, the larger the difference, the more polar the bond. So which bond is more polar between SO or HC or OH? So to answer that question, you need to calculate the electronegativity difference for each type of bond. So you look at your electronegativity table and find the values for S and O. So S is sulfur, O is oxygen. Oxygen is 3.5 minus 2.5 for sulfur, and that's a difference of 1.0. For HC, the carbon-hydrogen bond, carbon has a value of 2.5, minus 2.1 for hydrogen, that's a difference of 0.4. And for the OH bond, oxygen, hydrogen, oxygen has a value of 3.5 minus 2.1 for hydrogen, and that's a difference of 1.4. So by calculating those electronegativity difference, now we can classify the bonds as, from less polar to more polar. And here, the less polar is the HC bond, then SO, and then OH bond. So you classify them as more or less polar using the electronegativity difference value. So this electronegativity difference allows us to classify bonds in different types of bonds. And if the electronegativity difference between the bonded atoms is between 0 and 0.4, the bond will be classified as pure or non-polar covalent. So that's at the beginning of the scale to the left, pure covalent up to 0.4. If the difference in electronegativity between the bonded atom is 0.5 to 1.9, the bond will be classified as polar covalent. So from 0.5 to 1.9, it's polar covalent. And if the difference in electronegativity between bonded atoms is larger than or equal to 2, then the bond is ionic. So values of 2 or more in electronegativity difference will imply ionic bonds. So you will have these values to remember those limits. So when you have polar covalent bonds, we need to talk about partial charges, because the electrons are not transferred from one element to another. So it's not full charges that you would write as a pluses and minuses to the upper right of the elements symbol. Instead, we need to use partial charges, which are symbolized by delta plus and delta minus. And for example, HO, which is a polar bond, the electronegativity difference was 1.4. And so it's a polar bond, it's not ionic. So electrons are more towards oxygen. And so you have the delta minus on that side and delta plus on the other side, which is not the same thing as, ions like Na plus and Cl minus. It's not full charges. In a full charge, there is, one complete plus and one complete minus. In a partial charge, it's like a small percentage, a very small percentage only that creates, partial charges. So how do we know which atom will have more electron density? How do we know that oxygen will have the delta minus and not the hydrogen? So consider this representation of one of the two OH bonds in water. So the pink dots represent the electron density. So you can imagine that we know there is 2 electrons shared between oxygen and hydrogen. And let's say we are able to take pictures of them, one at a time, one picture at a time. And let's say you would superimpose all those pictures taken over some time. You could obtain this density plot where you see all the dots, and there is more dots around oxygen than hydrogen. And so this would show you the position of those 2 electrons, and they will be spending more time around oxygen than hydrogen. That's what this means. So the oxygen atom is getting the larger share of the electrons, and it will have a partial negative charge that we symbolize by delta minus, because it has the larger electronegativity value. That's what determines which one gets the delta minus. The more electronegative the element, the more partial negative charge it gets. And so the hydrogen atom, getting the smaller share of electrons, has a partial positive charge, symbolized by delta plus, because it has a smaller electronegativity. It doesn't pull as strongly on the electrons, and so it's lacking, if you will, some electrons, and then develops this small partial charge, positive charge. And so the result is this uneven electron sharing, right? You can see that they don't share equally. Oxygen has more the electrons around it than the hydrogen. And so it results into a dipole moment that is due to the separation of charge within the bond. So what is a dipole moment? The result of unequal sharing of electrons in a polar covalent bond is the formation of a dipole moment. And a dipole moment represents the difference between the positive center and the negative center, between the two atoms. So it gives you a measure of the size of the polarity of the bond. And it's represented by this blue arrow above the bond here. So polar bonds like the OH bond or polar molecules have one end slightly positive and the other end slightly negative. And so when you represent the dipole moment with an arrow, the arrow has like a positive sign on one hand. That's where you would have the delta plus partial charge. And the pointed end of the arrow points towards the delta minus. That shows where the electrons are pulled more. So here, the electrons are pulled more towards oxygen, and so the arrow points towards oxygen. It points towards the most electronegative element between the two. So that represents the dipole moment. So let's do a concept check to apply this knowledge. So for each of the following bonds, determine whether the bond is most likely non-polar covalent or polar covalent or ionic. If it is polar, you will need to indicate the partial charges and the direction of the dipole moment. So those dipole moments only are drawn for polar bonds, right? You don't do that for pure covalent bonds because there is no reason for it. And you don't do it for ions. It's only for polar bonds. So you can pause the video and do this on your own before you watch the answer, so that you learn to do it on your own before watching the answer. So when you have this bond between Na and Br, Na is sodium, Br is bromine, find their electronegativity values in the table of electronegativities. Bromine is 2.8, sodium is 0.9. So 2.8 minus 0.9, that's a difference of 1.9. And this is considered polar covalent, right? Up to 1.9, it's considered polar covalent. So you see that sodium is a metal, bromine is a non-metal, which we would likely classify as ionic, and it's borderline covalent, polar covalent and ionic. But according to the classification I showed you earlier, this is considered polar covalent. Now, if we have a bond between P and S, P is phosphorus, S is sulfur. Sulfur is 2.5 minus P is 2.1. That's a difference of 0.4. And 0.4 is considered non-polar. Oh, yeah, I forgot about this arrow. I told you earlier you need to indicate the dipole moment if you have a polar bond. And so for the first example here, NABR, I needed to show you how the dipole moment is drawn. and you point the arrow towards the more electronegative element, and here it's bromine. And so the positive end of the arrow is towards the less electronegative element, which is sodium in this case. Otherwise, PS is a non-polar covalent bond because the electronegativity difference is below 0.5. Okay, if we have a bond between calcium and chlorine, chlorine has a value of 3.0, calcium it's 1.0, that's a difference of 2. And that's just considered ionic. And we can confirm that calcium is a metal, chlorine is a non-metal, so we expect an ionic bond between the two. HN, nitrogen and hydrogen. Nitrogen is 3.0, nitrogen is 2.1, that's a difference of 0.9. And that's in the middle of the polar covalent range. So HN is a polar covalent bond. So we need to draw the dipole moment. The dipole moment is an arrow that will point towards the more electronegative element. So here, nitrogen. So the arrow will be like this, pointing towards nitrogen, because nitrogen pulls the electrons towards itself more strongly than hydrogen.